Now that we've learned how to quantify the effort or energy stored in a compressed or stretched material, specifically a spring, graphically, let's see if we can also determine an algebraic way of determining that. So let's go back to our graphical way of determining that. If we have, just in general, a generic spring that has some linear relationship between force and stretch, we said the slope is the k constant, or the spring constant. The area under that graph, or in this case the line, is the energy stored, which is the area of a triangle. So let's just say it's from its relaxed position to some amount of stretch, and to get to that amount of stretch, remember we calculate that by taking the spring constant times the stretch. This was Hooke's law. So the area under this line is the area of a triangle, which is 1/2 base times height, and that's equal to the amount of elastic energy or effort stored in that spring. So we have 1/2 times the base. Well, the base is just in variable form the amount of stretch, and the height of our triangle is the amount of force needed to stretch it to some amount of stretch. So just k times stretch. Well, like you see on the graph, that force can be calculated by multiplying k times the stretch. So let's substitute in place of Fs, or the force exerted by the spring, let's substitute k times the stretch, or the spring constant times the stretch. So we get 1/2 times the stretch times the spring constant times the stretch again. That can be simplified to 1/2 k delta x squared, or 1/2 times the spring constant times the stretch squared. So if you're stretching a spring, compressing it or stretching a spring from its relaxed position, the amount of energy or effort stored in that spring will be equal to 1/2 times k times the stretch squared. Looks like this. Remember, EEL stands for elastic energy stored in the spring. K stands for the spring constant, the strength of the spring as measured in newtons per meter. And delta X represents the amount of displacement or stretch of that spring, whether it's the compression or the amount of stretch. If we look at the units, if we're solving for an energy, remember we should get Newton meters, or which is also a joule. So we have 1/2 times k. Remember, k has units of newtons per meter. We're multiplying that by the stretch squared. The stretch in metric units would be meters. So stretch squared would be meters squared. So we get a Newton per meter times meters squared. The m in the bottom cancels out, and one of the m's up top does, so we're left over with Newton times meters. And remember, a Newton meter is a joule. So multiplying a spring constant times a displacement squared, or an amount of stretch squared, would give us some quantity of energy. Now if you're taking AP Physics 1, the equation on your AP Physics sheet looks just a little bit different. This is what it looks like. They have 1/2 kx squared, but they have this US. Now whenever you see capital U in your AP equation sheet, that stands for some type of potential energy, some stored amount of energy just waiting to be used. Well, this is the potential energy stored inside of spring or an elastic material, so they label it U sub S. We'll call that the spring potential energy. So the amount of potential energy stored in a spring is equal to 1/2 times k, the spring constant, times x, which they just use x to represent displacement or stretch.